introduction. Computational chemistry course, and class attendees present basic skills to use Gaussian software with the purpose that if any of us did miss something in the labs, through this recital, you'll get your knowledge more concrete, and you have chances to ask the presenter, so that we all, by the end of the meeting, we will be all on the same page, in the same board, knowing skills on the equal foot. So first presenter is Kia, and here are the subjects. So she will basically tell how to operate Gaussian software with GAUSSVIEW shell, while the rest of speakers will show something different. Okay, floor is yours. And I'll try, let's try to do 5 minutes plus few minutes for questions, if possible.
Okay. Thank you, Professor. So in today's presentation, I will show this thing. So let's go to the list of available electronic structure methods. So for the first thing, we need to build an atomic model using GAUSSVIEW software. So after that, we need to save the modeling input file. Then we need to go to the like there's option, so we need to choose that option, and after that when you want to change the method of that atomic model, you will able to see that there are several electronic structural methods, molecular mechanics, semi-empirical, Hartree-Fock, DST. So I wrote the full name of the all things here. So DFT is density functional theory, and molar plastic perturbation theory is this MP2, and those are things. So basically, in our lab, we most of the time we use molecular mechanics, Hartree-Fock, and today I will show another one. That one is density functional theory. So that three is more popular in the lab session. So the thing is, okay, let me explain something about molecular mechanics. So molecular mechanics is discuss about the force field. It is not very accurate. If you use this one, it will not give you the accurate result. Most of the time, we use this one to optimize our atomic geometry. So the second one is a Hartree-Fock method. So in Hartree-Fock method, there is a semi-empirical and the regular. So semi-empirical is quite it will give you the quite approximate result than before the molecular mechanics. But there is a problem is like you need to know the experimental value. Without that, you will not able to get the accurate result. And the regular one actually based on the mean field, and it discuss about the wave function. And then after that there is MPN. Why I wrote the MPN? MPN means just we need to go to MPN means that MP2 molecular plastic perturbation theory. So and that one actually used to improve the Hartree-Fock method by adding electron correlation effects by means of Schrodinger perturbation theory. So then the most common and the most popular structural method is density functional theory, DFT. So using this one, actually you will get the accurate result of the atomic model. If you want to see the IF or spectrum something, you will use that one. Okay. So the next thing, the next one is list of possible basis set and the nomenclature of basis set. So when you use first you need to set the method, then basis set. So basis set is it will show you how to actually show the electronic functions that are used to build molecular orbitals. So there are two types of basis set. One is plane wave and another one is atomic center basis function. So plane wave function, cos, sine and exponential, so that one is not used in our GAUSSVIEW software. We use just atomic center basis function. There are so many basis set of functions. You need to choose that which one you want to use. So first one is localized basis set. Localized basis set, and there is two type of local. Here I just show two types of localized basis set. One is flatter type orbital. Another one is Gaussian type orbital. So flatter type orbital will give you the more accurate result, and GTO, this Gaussian type orbital is more when you want to compare the two things together, then Gaussian type orbital will more give you result more faster than the latter one. So there are some problem with this. It's not a problem. It's actually I want to say that, and there are some limitation in this two orbital two basis set. That's why scientists they want to improve their basis set. That's why they use this equation, and after that actually they call it because they modify their equation, and after that they use this things, and then from that uh, like there are 3 to 1 g, that the 3 is actually define the inner shell of the orbital to actually give you the understanding of the Gaussian function of the first flatter or this flatter type orbital of the double zeta, and there are this one means is it will give you the function of summed up the second flatter type orbital. So in here you able to see that I used a term double zeta. So what's the double zeta meaning? Double zeta is like a function will give you the general idea of the atomic electron of the electron configuration actually. So as an example, it will if I give you on one example that will be clear for you, like in zeroth order, if you go to the periodic table in zeroth order, you will able to see that there is a single s function in the first, or if you go to the first row of the element, then you will able to see that there is a 2s function and one p function. And if I'm not wrong, then for the second row, if you go to second row of the element, then there is a 3s function and two set of p functions. Okay, so so there are another set of nomenclature of basis set. So and they modified their TO and GTO. After that, they got those things. Okay, there are after modified their if that equation I showed it before. Then they actually mm, yeah, got those things. There are for helium, sorry, for hydrogen, and if you want to see only this one, then you can use that one. And most of the time in our class we use that LAN L to D is that this basis set. Actually, it's everything is written in this website. I just copied from there. Okay. I want to show another thing that like okay. So after set up the basis set and method, then I need to optimize my atomic model. So for optimization, professor already showed that how to optimize the atomic model. And for optimization, we need to choose this one, and there obviously method will be used molecular mechanics and then, okay, just one. Okay, so after optimization and the uh, okay, after what happened?
I have a suggestion.
Yes.
You just summarize in words because if I know there is a really great material, but we
Okay,
will
okay.
fail.
Okay, just finish it, Ali. Then after optimization, you will need to, if you want to do the energy calculation, then you just choose energy and energy option, and for that method, you need to use the in HF method, and after that, like you want to see the result of that one, most of the time we use this few terms in Mobatics file, then we'll able to see the output of that result. But here is there is option, if you want to see the result, you can quickly check the your result there is, you will see the basis function. Then if you go down, then you will be able to see the energy as well. uh, okay, so in the last section, if you want to see the infrared spectra, then you need to choose a job type, optimization and frequency. You need to select this one. And for method, you need to choose the DFT. Here I didn't change the basis set function. So after that, I submit that file. Then I open the log file, and after that you just need to click the vibration part. Then you will able to see the result of this. Then if you want to see the just a minute, professor. If you want to see the result of that in a spectrum graph, then you just need to click the spectrum. There is an option like close, cancel, and there is option like spectrum. Just click that one. I just want to show in a quick view this, like this one. Here I select, oh my god, okay, it's working. So I choose the mode number 3 there in the figure. Then only that mode number 3 will started to uh, any image. If I choose this one, like there I choose one, it will show the frequency here. And after that, if I just 1 minute, 15, 15 mode number 15, and then if I click the start animation, then only 15 number mode will start to animate. See, like it's a molecule dancing like that. Okay, then
Okay, I suggest that we will finish now and
yeah,
maybe put
just
the rest of the time. Mhm.
1 minute, professor. Okay. So it's the end of my slide, and if you want to see the molecular orbit like HOMO and LUMO, professor like these things so much. So just you need to open the previous atomic model file, and just you need, there is an option like a red one and green one. It's the AMO or editor. AMO editor means molecular orbital editor. So you just need to click that one. After click that one, there is an option you have to like there is sorry you need to update your things there. If you need to click that one there, update. So after when you click that one, first okay, first you insert that one, then you will able to see that there is a 25 and 24. Then this one called homo and this one is lomo, and this one is +1 homo and the other one is -1 lomo. Lomo, yes. So there you already I already choose I want to show you 4 things. That's why I click the yellow but that's so that that arrow is this and this, that means up to the 24 it's occupied and the above one is unoccupied. So here we can see just minus minus the surface of the minus lumo, and I know we don't have enough time, just I want to show you the image video for that. Just a minute. Okay, so say when I click 30, that means lumo that it will show for 30, and when I click 29, then it will show you the surface of the atomic orbital for 29. Then if you click 28, then you will be able to see another images of that one. Okay, so that's the thing actually. It Professor,
Okay. Yes. Yes.
very difficult to finish these things within 5 minutes. It takes more than 2 hours.
Clear.
More than
Okay,
2 hours.
so please join. I invite everyone to join me in thanking Kia for very important and
I will
informative.
share with Professor a video, and that video will take more than 2 or 3 hours to explain the whole thing.
Excellent. Excellent. So, any very quick questions to Kia, or maybe we can postpone questions for the future.
Yes, you can send me questions through email. I can explain those things.
So, summarizing, Kia did show how to make molecular orbitals not in the command line but in the GAUSSVIEW, and she did show how to make infrared spectra, which we didn't touch in class, which can be useful for your projects. The decomposition of molecular orbitals over atomic orbitals will be hopefully continued in the last talk number 6 by Stephen. And with now, I would like Kaya, please stop sharing.
Yeah.
And let me invite Lola to make to present next. So please start sharing your screen. And I'll briefly introduce. So through very informative talk by Kea, you have revisited options to model and control things through GAUSSVIEW software. But sometimes, as you noticed, GAUSSVIEW connection may not work, and we need to learn how to be independent, how to do the whole cycle of research without touching any graphical information. And Lola Eniadunmo will teach us some basic steps of doing Gaussian calculations without graphical interface completely. So floor is yours.
Okay. Good morning, everyone. So I'll be sharing how to do some of the things that we do in GAUSSVIEW. We'll be able to use command lines to do them instead of using GAUSSVIEW. I would also indicate the memory of what I'll be working with, the number of the processors, as well as the spin and multiplicity inputs. Now, first of all, I'll be working with a text.com file, and a text.com file contains the position of the component that make up a molecule. So first of all, I'm going to be I created the XYZ model of hydrogen molecules. So I'm taking hydrogen as my case molecule here. So this command here, vi h2 and .xyz, helps you to create the H2 molecule. So now here I'm defining what the molecule is going to be. So it's going to have 2 electrons, and I'm specifying this coordinate for the 2 hydrogen atoms. Here I wanted to be sure of the content of the H2 molecule that I created. So I did more H2 and .xyz. So this is what it showed up as the content, which correlates with what I initially created. Now, I decided to convert it to PDB, which is going to be readable. So I use this command, Babel IXYZ here indicates where I'm coming from. That's the format of what I initially created. And this OPDB means I want to convert from XYZ to PDB. And I'm telling it here to convert to PDB. Now, this message here shows that it has been converted. So here, converting the XYZ to PDB using Babel. So like I mentioned initially, this is the message indicating successful conversion to PDB. This here indicates the format that I wanted to convert, and here indicates the format that I aim to convert to. Now, I try to read the H2 molecule I created in PDB this time. So if I do more H2.PDB, this is what it comes up with. Now it's indicating the 2 atoms of the hydrogen as well as the XYZ positions that I defined earlier at the beginning. Now, just a little bit of flex, I decided to go from PDB to XYZ using Babel just to confirm that I have the same thing on both ends. And as indicated here, I had the same thing. So it's the same thing here. From PDB, I want to go to XYZ. So I'm converting this to this. So it shows that I still have what I created initially. So now, viewing this same PDB file as here, you're going to get a result that shows the memory of what you created, which is 15 gig, and the number of processors, 8 processors. This information comes with this right here. It's just, you just have to scroll down and then you see this. So sorry, yeah, I use this command line actually to come up with this memory and number of processors. So right after the XYZ positions, I just did more this command line and it shows me this. Now, spin is a property of electrons and it's a form of angular momentum. Now, multiplicity is the number of possible orientations that the spin angular momentum can take. It could be singlets, it could be doublets, it could be triplets, and so on. So I'm trying to look for the multiplicity of the molecule, the H2 molecule that I created. Now I'm going to merge the XYZ file with the .com file. That's what this command here helps me to do. This cat here means to concatenate. So I'm merging the h2.xyz that I created earlier with a test h2.com file. Now I want to view what this h2.com file is. That's why I have this command right here. So as you can see, the h2.com file still has the initial 15 gig memory and the 8 number of processor. Now, this is generated as initially the XYZ coordinate that was defined. Now, it now shows up this number at the top. Sorry, this is meant to be charge, not spin, sorry. So right here is 0 charge. The H2 molecule has a charge of 0, and the multiplicity unit here 1. Multiplicity can also be gotten from an equation which is 2s plus 1, where s indicates the charge. So if the charge is 0, the multiplicity is 1, which we've already gotten here. So there are some parameters that we could also get. The same parameters that we get when we use GAUSSVIEW can also be generated through command lines. Now, so here, after I decided to open up and see what the h2.com file contains, and it has a line here that is requesting to run Hartree-Fock line 2 DZ for the H2 molecule. So now this is what we had initially, the 0 charge and multiplicity unit of 1. Here, the XYZ positions as indicated initially. So what I tried to do was to run this command, go9 test h2.com. Apparently, it converts it to this cation.com. And then I wanted to see the content of this file. So I did ls-lt, and it shows me that it has converted my .com to chk and to log file. So remember that even in GAUSSVIEW, we always click on the .log file to see all the information that we require. So what I tried to do was open up this .log file. So that's what I did with the more h2 cation.log file. So when I opened it up, this is the result that I got. I still got the 15 gig memory space, the 8 number of processors. I have the charge 1, multiplicity 2 as initially, because now in this context it's H2 cation, so it's H plus in this case, not like the 0 for the H2 molecule that we had initially. So now if you scroll further, you are going to see this total energy right here, which we normally get when we use GAUSSVIEW, when we try to run the Gaussian calculation. Then right here we see the occupied orbital has this energy, and then the virtual, the beta and the alpha, which initially we would have done by linking GAUSSVIEW to MULTIPLICITY. So yes, that's all. Thank you very much.
Okay, please join me in thanking Vola for a nice and useful presentation. If there are quick questions or corrections, please speak.
Hi, may I know that which software you use?
Still MULTIPLICITY.
It's mobile.
Yeah.
Okay, let's maybe ask additional questions through emails or chat line. And by the way, if while listening the talk you are developing questions, you can type them into chat line and then the speaker will see it. And now let's thank Lola once again. I think it is really, really useful for all of us. And the next, through first 2 speakers, you learn how to launch Gaussian job. The next, I may suggest next you will. Okay, Lina, if you want,
I'm okay if you suggest another person, so I can stop sharing.
No, keep going, keep going.
Okay.
And now we'll start analyzing output of the Gaussian. What can we learn and how we can characterize materials? Okay, floor is yours.
Okay. Good morning, everyone. Today I will present 2 main points: how to analyze the output of the log file without using GAUSSVIEW, and through that I will show you how to extract some parameters like the total energy, ionization energy, electron affinity, and the hollow gap. And then how the results depend on the choice of the basis set, which was explained by Kia in details in the first presentation. So first, let's see how to analyze the output log file. So after building the atomic molecular model, and now you want to see some information about your model, you can just type this command. I use the file name. I should put monomer underscore hf.log. So here monomer underscore hf is the file name that I use. And then you will see this screen. And if you see here, you find more 8%. So far it's showing just 8% from the information that you need. So clicking the space many times, you can get all the information about our model. And here I just give you just portion of the information. And so then I will show you how to extract the total energy. So here we can use this command, grep scf with the file name .log. So it will go directly and show you. So this is the command to extract the total energy directly. So even you can scroll here in this screen, you can find everything you want. But if you are hurry and you want to see them, to see some parameters quickly, so this command helps to just show you the total energy right away. So here we have the total energy in the yellow square, and it's simple. And then for the ionization energy, this command helps you to show the occupied states. So it shows all occupied states, and in just using one command. And the last number here is represents the ionization energy, as it's the last occupied state. And here how you find the ionization energy. Simply the electron affinity, we can use this command to extract the virtual states, because the electron affinity value would be in the first value here, the first number in the virtual states. So this number called electron affinity. And simply how to get whole low gap. So going back to the information that's provided using the more command, you see the occupied states and the virtual states in the same page. So taking the ionization energy and the electron affinity, so just subtract these numbers as follows, as here it's whole minus low values, and this will give you the gap energy. Of course, it will give you the gap energy in the atomic unit, and to calculate it in electron volt, which is more practical unit, just you can multiply by 27.12, and it will give you the value in the electron volt. Here the second question, how results depends on choice of the basis. So Kia explained all the possible basis sets that we can use for explaining, for applying in our model. And another time, just to define the basis set, what the basis set is just the functions that we use to represent the electronic wave function. And there is some types of the basis sets that we use. For example, the minimum means that the basis set describes only the most basis aspects of the orbitals, and each function has a different shape than the other, which is should be appropriate for the model that you use. So how to choose the different basis set? so this list will show you all the possible basis sets that you can use, and the names here just indicating the approximated atomic orbitals that used for your model. And I'll give you just some examples. For example, C21G explained in details also by Kia, but it just generally it splits the electrons, for example, in the core and valence electrons. How this is how it approximated the function used for the wave function for the electrons in the model, because these functions represents the single particle states, and the combination of these functions would give us an idea about how the electrons or how these particles in this model behave like wave, or how they behave, and this will describe our model. And by solving using these functions, we can get the results and the results that we want. Another example here, I just use CCBVTZ. It's correlation consistent, correlated valence d zeta basis. We used, for example, in the class LAN L2DZ, which is LAN is abbreviation for Los Alamos National Laboratory, which derived this function and maybe established it for 2 double zeta, and it's mostly used to model the metal atoms. So because of that, we used it in our in the lab, depending on the model or the molecule that you build or you want to represent. So if we choose different, what's the difference between, or what's the result can be, how results can be affected using different basis set? Of course, when you apply the function and the basis set to your model, for example, here, looking at the summary, you can find the total energy and some other information about your model. The same model I used 321G or LAN L. I know it's not reasonable to use to apply many on just one model, because each model or each molecule has to there is an appropriate model best fit with that model to describe it perfectly. But just to show you the difference, we have different numbers and the total energy, so the outcomes would be different using different basis set. And to be able to use the appropriate one, I think it needs like experience and enough knowledge to decide about each basis set and each function, how should it describe the model and to be the most appropriate one for the model. So this is what I want to show. I think our presentation 5 minutes. I want to go beyond of that. So this is all the things that I want to show today. And thank you, and welcome if you have any questions.
So please join me in thanking Lina for a nice presentation and an interesting analysis. If there are quick questions, please do not hesitate to ask right away. And I have a quick comment. If one focuses on band gap, then it will be much less dependent on the choice of basis set. Because total energy depends on number of basis functions and number of actively counted electrons, but gap is not. Then the difference will be not like 3-5 times. It will be just a little. More any questions? 1, question 2, question 3. No questions to Lina. Let's ask her once again. And we have 18 minutes for 3 talks. Next presenter is Boston, and he will teach us how to summarize information about orbitals into graphical format. And again, he will continue a trend to analyze data without GAUSSVIEW. floor is yours.
So can you see the screen? Just making sure.
Yeah.
Okay, perfect. So hello. As Dr. Killen said, my name is Boston Hayford, and I'll be talking about extracting and plotting density of state data with Perl and GNU plot. So to extract your data with Perl, first you need to obtain your .log file from whatever system you're working on. You can use the methods we've done in class, such as using GAUSSVIEW, GUI, or you can do like Lola was just talking about today, you're doing like command line stuff. And once you get your .log file, all you really need to do is use the command Perl with this string here, which is just a Perl script that was developed probably by Dr. Killen, I'm not sure, or someone else. And it does some things under the hood that extracts your density of state data from your .log file. And it depends on these 4 different parameters that you can give to the command. And so A is the number of steps taken in your density of state data. So the more number of steps that you include, the sharper or higher resolution your density of state will be. B would be like the bandwidth, which I believe, and Dr. Killen can correct me if I'm wrong, but I believe that's essentially how big your bins are in your band gap. So a certain range of energy that you're including in each step. So again, the smaller you make that, the kind of sharper resolution your energy gaps will be. So it won't look quite as blended as it would be if you have a larger bandwidth. I'll have a couple pictures in just a second here. And then 3 is how far below the highest occupied molecular orbital you want to plot. And then D is how far above the molecular orbital, the lowest unoccupied molecular orbital you want to plot. Just to see a little bit more information on how to actually apply this stuff, if you are working in the Photon server, at least, I doubt this will show up in any other server if you're working with there. You can use the command more, and then that string that's down there. And if your system that you're modeling has an odd number of electrons, the above steps that I just kind of went through aren't exactly what you need to do. You need to do something slightly more different. And you can find more information on that using that command. It's very similar to the even number of electrons, just a little bit more involved, but not by much. And so after you run your Perl commands, it will return 4 different files. It will return this density of state file, which has this B. That's, if you remember back, that is the bandwidth of your density of state files. And then your file name, and it'll give you this E with your file.log, and this eVirt and eoc files. So this density of state file, that's going to contain all the data that you're going to need for your density of state plot. It should include 4 different columns. And then your E underscore your file.log contains columns of the number state, energy, in electron volts, energy in atomic units, and then the occupation state. And that is what I have pictured over here on the right. This is the E file. And then eVirt and eoccupy just contain the virtual and occupied eigenvalues, respectively. So that will be the results from your Perl commands. And that's pretty much all the information that you're going to need to actually use GNU plot to make your plots to do your to view your data. So to plot with GNU plot, once you have extracted your data with the Perl command, you need to do the following. This is the script method. So this is, again, a pre-made script you can run that will just extract all your data and plot it for you, which is very useful, but I'm going to be talking about the manual way to do it a little bit later. So what you need to do is you need to copy your density of state file that you got from Perl into a new file called dos.log. Just renaming it there so you're not actually doing any different kind of calculations with it. And then all you're going to need to do is to create the DOS plot by running the command GNU plot followed by that string there, and then you'll have an output that is this dos underscore go9.ps. Now the ps file is in older.
Sorry, please wrap up. You're already speaking for 5 minutes.
Okay, so yeah, so then to change the output file is just use that command right there. And then so to do some manual GNU plotting, you can follow these commands. I won't go them through in detail, so I can just wrap up here real quick. And then you can do some more commands to add lines. You can do some more commands to add plots and titles and labels. And then you can do a bunch of other things to change the columns that you're plotting. And then there's a bunch of other stuff you can learn about as well. If you just Google GNU plot, it'll give you lots of functions. And then once you have done all that, in order to save your plot manually, you can run these commands and then finally switch or convert your output file to a PDF. So thank you.
Okay, please join me in thanking Boston. It is a vital skill which all of us need to practice for next homework due Tuesday. So any quick questions? 1, 2, 3. No questions, but thank Boston once again. And we have 2 more talks for 11 minutes. So the next presentation is by Sarah, and she will teach us how to plot pictures of molecular orbitals, which is also needed for the homework due on Tuesday.
Thank you, Dr. Klein. Today I'm going, hello everybody. Today I'm going to talk about molecular orbitals, how to plot them in both GAUSSVIEW and OpenShell configuration, and some concepts about the isosurface and the isosurface of total charge distribution, potential and molecular charge analysis. The first slide is about the concept of isosurface. Let's see what's the isosurface mean. Actually, the isosurface represents points of constant value like velocity, density, temperature, pressure within a volume of space, and it's a level set of a continuous function whose domain is a 3D space. As you can see in the 2 pictures below, the isosurface of vorticity trail from a blade, and then we have the next one, which is the isosurface of total charge distribution. Let's see what is the charge density means. At first, it's the amount of electric charge per unit length, surface area or volume, and it the isosurface charge density, which we show it by the sigma, is the quantity of charge per unit area at any point on a surface, charge distribution on a 2-dimensional surface, and its unit is a coulombs per square meter. As you can see in the 2 picture on the top and the bottom, there are isosurface are for the water and the silicon that represented as in a unit cell. The next concept is a molecule population analysis. The molecule charge arises from this molecule population analysis, and it provides a mean of estimating partial atomic charges from calculation carried out by methods of computational chemistry, particularly those based on the linear combination of atomic orbitals or molecular orbital method. As you can see in the picture, it's a fluorine molecule, and I'm going to talk to show you how to plot the molecule charge distribution in the GAUSSVIEW. After opening your model in the Gaussian, from the result tab, you may choose the charge distribution, and you may choose the type of the atomic charge, which I selected molecule, And after choosing the show numbers and color atoms, you can see the charge distribution on the fluorine. The green atoms show the less electronegativity, while the red one shows the more electronegativity. The next concept is the molecular orbital. In the chemistry, molecular orbital is a mathematical function describing the location and wave-like behavior of an electron in molecule, and also they are the linear combination of atomic orbitals. As you can see in the picture, there are occupied and virtual molecular orbital for the actylene. Now let's take a look for how to plot molecular orbitals in the GAUSSVIEW. To do this, to this end, we need a cube file, because the molecular orbitals are stored in the cube file. So to create the cube file, we need to execute form check to create FCHK file at first. After executing this command and executing ls-lt, you can see that you have FCHK file added to your directory. So after getting this file, you may execute the CubeGen command. So CubeGen O stands for orbital, a molecular orbital number. For example, here I selected 24 molecular orbital, and the name of the input file FCHK, and the name of output file that you desire to save this file. Again, after executing this command, by executing ls-lt, you can see that you have the cube file for this molecule. For the plotting the molecular orbitals in the Gaussian, after opening the GAUSSVIEW software, from the result tab, you may choose the surface or contour, and from the surface available, you can choose the new surface. And here for the molecular orbital, you choose the number of the probability or the size of the cloud. The higher number you put in here, the smaller probability or cloud size you will get. So you can see in the bottom the molecular orbital for the fluorine. And the last slides refer to the plotting the molecular orbital for open shell configuration. If we change the multiplicity and charge, we end with two orbital, alpha and beta orbitals, which stands for up spin and down spin. As we have in the lab in this previous session for the lab, for the titanium with 6 water molecule, you can see that after minimization, after energy calculation and opening the log file, you can see that we have two type of the spin, alpha and beta. Both have occupied and virtual situation or orientation. So here again with executing CubeGen, and but in this state we have AMO and BMO, which stands for alpha molecular orbital and beta molecular orbital, and the number of the molecular orbital that you desire to plot, and the name of the input file, and the name of the cube file that you wanna to save it. And as you can see in the picture, again, the same procedure for opening the cube file in the GAUSSVIEW, as I explained here in this slide. Again, you may choose result and surface or contour, tab and choose new surface and plot these two beautiful molecular orbital. And in the Thank you for
thank you for presenting. Please join me in thanking Sarah. It's a very useful skill, and please use it for completing the homework, making HOMO and LUMO orbitals for progression of 5 titanium dioxide oligomers towards Tuesday. And now in the remaining 3 minutes, we have the last but not least talk of Steven Westra. And he will connect presentation of Boston and presentation of Kia into a single thing, showing us first steps how to analyze decomposition of molecular orbital over atomic orbitals. So please start sharing screen. Do you have co-host privileges?
I do, but I need to make sure I have the right thing selected. I think. Let me know if this is unreadable for anyone. This is on a wide monitor.
We see an invitation to ask questions.
Oh, that's the last slide. All right. So, as Dr. Killen said, I will be sort of connecting two ideas, and that is we can learn how to take the density of states of a whole molecule, but in some cases you would want to take the density of states of part of a molecule or parts of a molecule. And so, to take the density of states of parts of a molecule, there's really just a minimum of one step additional that you have to do, and that is you have to select what fragments that you want to calculate it as. Other than that, everything is the same. And now if you see on the right side with the molecular geometries, you can see that after each atom there's a parentheses that says a fragment and then a number. And also the charge and the multiplicity is much larger. That is, respectively, the first two are the same, the charge multiplicity of the whole molecule, and then each one after that is what you are giving as the charge multiplicity for each fragment. So to select multiple fragments, there's one very easy thing to do that I unfortunately was not able to show because it's a pop-out menu, but you go to the Edit tab in GAUSSVIEW, and then you select the Edit tab, and then the inside of that, the Edit Again tab, and then there's atom groups. So if you click on that, it'll open this window with GAUSSVIEW, and then you just need to enter the number of atoms, or the atom number that you want to move to that fragment. This is based on the list of atoms from your input file. So titanium is atom number 1. So it's 1, and it's the only atom in fragment 1. And then you do that with the rest of them, and that will determine what fragment they go into. And then after that, it is just the same as any other DOS calculation. And as Boston said, at that point you would do any appropriate post calculation processing. So, and then on the right here we have a density of states for what I believe it should be the titanium atom.
Is it the right slide, last slide? Before
yes.
your okay, so I believe it was the different version. So let me bring maybe the most updated version of your slide. So here is what Steven wanted to show in his last slide. The different colors correspond to different contributions from different types of atoms. So here red corresponds to oxygen for occupied, then black corresponds to titanium, and blue, which is not shown because it is out of the site, would correspond to hydrogen. So with this, let me invite everyone to say thank you to Steven. And we are going to close this session. So let me summarize that through your outstanding contributions, we covered most of the practical skills for use of the Gaussian and Gaussian for the research. There are two things that we are missing, and maybe we will cover them to the end of the course because we need to start another software. So missing things that we didn't learn yet are how to model chemical reactions with Gaussian via scanning of potential energy surfaces. So if you are looking to further master your skills in Gaussian GAUSSVIEW, look for the scan of PES to model reactions. And another thing, to model optical spectra with so-called TD-DFT method, which I hope to cover by the end of the class. So I would like to take opportunity to thank all presenters and also visitors. Because of the format, there were no time to ask questions, but our meeting was supported by Professor Kikan Jan from engineering, Professor Bakhtiar Rasulev from coatings and polymer, and by Dr. Mohammed Javed from University of North Dakota. So many thanks to everyone. Meeting is done. Everyone is welcome to disconnect, and I will stay connected just in case there will be some individual questions to ask. But it's great success. Many thanks, and looking forward to see you again on Tuesday.
Have a good day, everyone.
Thank you. Have a good weekend.
Have a nice weekend, you too.
Thank you.
Have a nice
Bye.
weekend. Thanks, Doctor. Bye.
Bye. Thank you.